Aeronaut X. I love that cool new logo. We are looking at electricity circuits in the X57 Maxwell. But before we take a look forward at the X57 Maxwell and what's coming, I want to start with the leading edge of flight, which is a NASA video talking about the 60 years of flight. So in our first 60 years, what we've looked at.
The design concept reduces the drag at transonic speeds, allows the airplane to fly faster and farther.
We've actually done aeronautics research for over 100 years. So NASA's predecessor was the National Advisory Committee for Aeronautics, the NACA Field Laboratories, and became part of NASA. And we've continued that tradition.
They developed a lot of the theories for the people they had back there. They developed wind tunnels. We ran the wind tunnels actually 3 shifts a day because there was that much demand for the data from the companies, and that's who we were doing it for. We had lady computers who reduced the data for us.
Ready to launch now.
The X-15 was, in many ways, the ultimate research tool. The very first aircraft to fly into space and come back and land horizontally on a runway.
We had to make the engine run in order to make the plane fly. It had to be dropped from altitude, it had to be started at altitude, and it had to have stable combustion, and we made it work.
It was very much an experimental, one-of-a-kind laboratory in the sky to investigate the next great hurdle, which was hypersonics. And that's a problem we're still working on today.
So we've always been trying to go farther, faster, higher. That's what mankind has always wanted to do, to explore. That's what NASA does, we explore. And now NASA's looking at a new X-plane so that we can make it a little bit easier to get across the country, about twice as fast.
And the innovation there is actually the shape of the aircraft so that we can enable supersonic flight over land, and that'll open up a whole new industry.
Here we are looking at how do we take all of those things that we've learned historically and place them in an aircraft that can actually fly faster than the speed of sound without creating the sonic boom. And if we can accomplish that objective, then people all across the United States, and in fact all across the world, will be able to fly faster than the speed of sound, and in fact they could fly multiple times the speed of sound without disrupting communities on the ground. We want to be at the very leading edge of technology when it comes to supersonic flight.
When you look out that window and you see that winglet, that was developed originally by NASA. There's so many things that NASA has done that we're with you when you fly.
The computers used on the space shuttle, the prototype of those computers were actually flown on the F-8 digital fly-by-wire airplane.
80% of the world's commercial airliner fleet today use that same technology in order to fly their aircraft. And almost all the military aircraft that are made today.
I remember the first time I was flying an F-18 Hornet, I was in a bit of turbulence and I thought I was holding the airplane steady and my flight controls were moving. Well, those technologies and those capabilities were developed by NASA.
Electric propulsion is really just opens up the playing field for what you can do with airplanes. Vehicles that be an air taxi type vehicle where 2 or 3, 4 people would travel across a downtown area and be able to get to a destination much quicker than being stuck on the freeway. And so it's going to create all new types of designs for vertical lift, transitioning to forward flight. And the predictions are that we'll be 3 times more efficient.
Unmanned aircraft systems follows in a long line of technologies that NASA always is pursuing to improve the quality of life for your everyday person, like to examine bridges or buildings that perhaps were damaged in an earthquake, find out where the damage is, could do that by never having to actually go into the building or walk on the bridge. So that makes it safer for people.
RTP straight. That's 836 Roger straight.
For 60 years, we've been exploring. We stand on the shoulders of giants that came before us. They figured it out, and we take it a little bit farther, a little bit farther. It's what we call pushing the envelope when you're a test pilot.
So we've done a lot of things in the past 60 years. Probably one of my favorites is, yes, NASA is with you when you fly, and seeing those little winglets on the airplane, quite an innovation that NASA can be attributed to. So the X-57 Maxwell, that's going to be our focus today. It's a small experimental airplane powered by electricity. Its all-electric technology will make flying, hopefully, cleaner, quieter, and more sustainable. So as we talk about it being an X-plane, I do want to show you a video. X-planes are experimental planes, and they can also be experimental rockets, and they test new technologies and aerodynamic concepts. And here is a video that gives you a look back at the history of X-planes, and then also focuses on some of our newest, the X-57 and X-59. Again, the link is in the chat if that proves to be more efficient for you.
That's one small step for man, one giant leap for mankind.
History is about to repeat itself. Over the past 7 decades, the nation's best minds in aviation have designed, built, and flown a series of experimental airplanes to test the latest imaginative and cutting-edge ideas related to flight. Short wings, long wings, delta-shaped wings, forward-swept wings, scissor wings, big tails, no tails, high speed, low speed. Individually, each of these pioneering aircraft has its own story of triumph and setback. Together, they are known as X-planes.
Each of those X-planes has an interesting story all of its own. They've all made an incredible contribution to our understanding of flight. And X-planes are really cool.
On October 14, 1947, Air Force Captain Chuck Yeager climbed into the bright orange, glamorous Glennis and flew the X-1 into its moment in history. The Bell X-1 was the first plane to fly faster than the speed of sound, thus breaking the sound barrier. Perhaps of all the X-planes NASA has been associated with, none was more cutting edge and became more famous than the X-15 rocket plane.
The X-1, it's the most famous because it was the first to go supersonic. But the X-15, it was the most productive of our X-plane programs.
Flown between 1959 and 1968, the winged X-15 reached beyond the edge of space at hypersonic speeds. Trailblazing design concepts that contributed to the development of the Mercury, Gemini, and Apollo piloted spaceflight programs.
That's one small step for man, one giant leap for mankind.
History is about to repeat itself again, and humans will take another giant leap. NASA is building a new generation of X-planes. The first all-electric aircraft, the X-57, will increase fuel efficiency, significantly reduce carbon emissions, and reduce unwanted noises. The newest X-plane, the X-59, will be an aircraft that flies at supersonic speed. But instead of creating the annoying sonic boom, creates a quiet sonic thump.
The X-59 aircraft is an exciting addition to a long history of X airplanes, including the X-1 and the X-15. NASA is working with Lockheed Martin to design, build, and flight test the X-59 aircraft. It's going to be about 97 feet long, fly at a Mach number of about 1.42, which is roughly around 900 miles an hour. It's got a long nose, engine on top, highly swept wings, and a very carefully shaped fuselage to enable that low boom flight that we require for this airplane. There's really 3 phases on the low boom flight demonstration mission. The first one is we need to make sure that the airplane is safe to fly and to fly in the United States airspace system at about 55,000 feet. Second of all, we need to do validation flights to show that the airplane can fly in a variety of flight conditions and atmospheric conditions. And then the third phase is really this community response data, where we go out and get the data and provide this data to regulatory agencies such as the FAA so that they can lift the ban on commercial supersonic flight.
The success of the X-59 could be the next giant leap for mankind here on Earth. This means one day in the not too distant future, you may be flying on a supersonic commercial flight over land, getting where you need to go in half the time. How cool is that? Remember, NASA is with you when you fly.
I think it would be totally cool to go supersonic over land. They say that that'll actually potentially cut air flying time in half. So lots of history there with the X-plane. I will kind of tell you that X stands for experimental. You may have heard of the B-52. B is in bomber. The F-18 or the F-16. F as in fighter. The C-120 or C-17. That C is in cargo. You can do a quick little internet search to find out what the other examples are, but X is for experimental. So X-planes of the future, you know, NASA's looking at using computer modeling, scale models, wind tunnels, and prototype test flights to design and test X-planes. Where do we go from here? Well, these new technologies, and the focus is technologies, not aircraft. NASA's not about building one airplane that's going to be replicated many times. It's about building the technologies. NASA researchers are looking at ways to improve aircraft, not reinvent them. As an example, here this photo, NASA researchers use the Schlerin photography to better understand how airplane produces shock waves. So just amazing ways that NASA is using technologies to help improve aeronautics and flight. Some of the new challenges. How can we reduce noise? I don't know if you've ever lived near an airport or been around an airport, but airplanes taking off and landing, they're not quiet. And the sound created by the air flowing around the landing gear, they're looking at ways to reduce that noise. We've looked at lower fuel usage, looking at lower emissions, more ways to become green and to take care of our environment. So definitely new challenges we're taking a look at. But what we want to focus and look at today is the X-57 Maxwell. And here is a short little video clip to kind of introduce us. It'll share you a little bit about the wings, and also talk, I think, a little bit about the electricity aspect of it. Here we go. Why build an electric airplane? Electric power is efficient and reliable, and electric motors can be placed anywhere on the plane to help improve efficiency. Now, the propulsion aspects of electricity, there's no fuel, therefore there's no combustion engine. It's powered 100% by a cutting-edge distributive electric propulsion system. As far as the environment, how does this distributive electric propulsion technology stack up against their traditional piston engines that fly on airplanes? Well, take a look at the average operating cost per hour. Take a look at the average cost of fuel per hour. Yeah, electricity totally wins there. The percentage of operating cost per hour for energy. And then, does it produce greenhouse gases? No. So it's cleaner, it's greener, and it's cheaper. And did you know that general aviation planes use leaded fuels? That cost about twice as much as auto fuel. Whenever I was a kid, and I may be dating myself, I can remember whenever you would go to the gas station and you could get either regular or unleaded. And that regular fuel was leaded fuel. And but I can also remember I think it was in the late 80s that they did away with that leaded fuel, and we went to what's called unleaded. Now, nowadays, all that's available for cars now is unleaded fuel, but we no longer call it unleaded or regular. It still just has the name of unleaded. But the fuels that the planes use are still leaded fuel. So the engines, electric motors are smaller, quieter, and lighter, but transfer less power than combustion engines. So that's a drawback. But the X-57 has 14 electric motors instead of 2 piston engines. So why, you may have heard me saying X-57 Maxwell. Why has it got the nickname Maxwell? X-plane nicknames are often proposed by the program team, and the name Maxwell was proposed by the principal investigator Sean Clark, and his proposition for naming it that was due to James Clerk Maxwell, who was a 19th century Scottish physicist, and he pioneered the theory of electromagnetism, which paved the way for Einstein's theory of special relativity and Planck's formulation of quantum mechanics. And so if you hear the X-57 called Maxwell, or you hear it X-57 Maxwell, we're giving a little hat tip to James Clerk Maxwell from the 19th century, and that name was picked or suggested, proposed by the principal investigator for the X-57 project, Sean Clark. Just a little, did you know? I don't know, maybe that'll be on Jeopardy someday. So looking at the X-57, NASA's X-57 Maxwell will be the first all-electric X-plane, and it'll be flown to validate and demonstrate the benefits that distributive electric propulsion may yield for the future of aviation. The goal of the X-57 is to demonstrate a 500% increase in high-speed cruise efficiency, 0 in-flight carbon emissions, and much quieter for the community on the ground. There is an X-57 lithograph, and I will give that as a PDF for you at the end. What you're seeing there on the left is the front side of the file, and on the back, you've got the 3 different pictures there, and that's showing you Mod 2, Mod 3, and Mod 4, and I'll explain to you what those mods are. But it's also available in Spanish, so if you happen to have Spanish-speaking students, we have this litho available in English or Spanish, and I'll give you the PDF versions of them at the end of our presentation today. So, Mod 1. This is the first phase of the X-57, and yes, you're seeing it right there in front of you. They tested the potential for electric propulsion. The project on the ground was originally called Leap Tech, and those Leap Tech ground tests were conducted on the lake bed outside of NASA's Armstrong Flight Research Mission Directorate in California. And so they put the wing with the motors there and mounted that on the back of, I don't know, part of an 18-wheeler, or I guess maybe a semi-truck is how I should say that, and ran that down the lake bed to see the potential to see how those motors would react. And you can see part of the Mod 1 team. We call it Mod 1, but what Mod stands for is Modification 1. So the first modification was putting the wing out there and seeing how it aerodynamically went. as far as whenever we did the test just going down the runway. Mod 2 is actually with the actual airplane. So this second phase includes both ground and flight test. So electric motors, batteries, and instrumentation, and some of the technology being tested in this section. A new wing designed to accommodate 2 new engines has been developed. Now, if you'll remember from the video, we didn't create this plane from the ground up. We took an already common plane and we modified it. So the new wing design is being developed, but it's not yet flown the X-57 at this stage. How do I know that? Well, if you'll notice, this here has the typical engines close to the fuselage, whereas the X-57 other modifications, you've got not just engines up and down the leading edge of the wing, but also at the end. So Mod 2 here is where we do the flying with just those 2 engines, but we have added the electric motors, we've added batteries, and we've also added other instrumentation. Mod 3, now this is where that new wing design, so take a look, Mod 2, Mod 3. Can you see how the wing has taken a new shape? I'm going back and forth here. So the wing has taken a new shape. In addition to the new wing design, it's repositioned the motors at the very end. And this phase, which overlaps with modification 2 and 4, includes building and testing additional components for the final version of the X-57. So you'll notice that we have in Mod 2 the place for the other motors to go that'll go on the wing, but right now we've got the heavy lift ones on the very end. The motors that go on the wing are called cruise motors. The ones on the end are called heavy lift motors. So Mod 4, this is where flight tests that include all 14 motors, and they're the major part of the final phase of testing. The 2 large electric cruise motors are already tested, and those 12, I said it differently, it's the 12 or the smaller high lift motors will be integrated into the wings. So whenever they are just cruising at altitude, that's when we'll have these 2 cruise motors. It's the 12 smaller motors here that we use to get the lift whenever they are at takeoff. Sorry for saying that differently. I've got a better picture here that identifies the different motors. So each wingtip has a large electric motor because it takes a lot of lift to get the airplane off the ground. And in taking that energy to get off the ground, or that lift, we'll use those 12 small electric motors. Now they have fold-in propellers that are on the front edge of the wing. And so once we get up to altitude, those 12 small electric motors, which are our high lift motors, those propellers will fold in, and then we'll just have our cruising engines going at that point. So what will it actually look like in flight? I have a short little simulation. And again, this is just in simulation, as I think we're currently still at Mod 3. So at takeoff, all 14 engines are going. Once we get to altitude and we just want to maintain flight, you'll see that the heavy lift motors, those go back. And then our cruising motors help us to cruise at altitude. Can batteries power an airplane? Well, seeing as how we're looking at an electric airplane, we hope so. But batteries power everything from your cell phone to equipment on board the International Space Station. And the X-57 Maxwell will use rechargeable lithium-ion batteries. When batteries are charged, electrical energy is converted to stored chemical energy. When a circuit is completed, the electrical energy is released for use, and the battery loses charge. And I don't know about you, but I have to recharge my cell phone every night because I use that battery every day. So Speaking of lithium-ion batteries, here is a short little video about how does a lithium-ion battery work. And again, that'll be the type of battery that's on board the X-57 Maxwell. So a simple little process to understand how batteries work. Looking at the X-57 battery setup, here's a picture of a 50-pound battery pack, but we'll be using commercial lithium-ion in two 400-pound packs. So this 50-pound pack is 8 times smaller than the 400-pound pack we'll have. We will place it inside a custom-designed battery packs. It'll be located in the cabin, and it will supply 23 kilowatt hours of energy. Extensively tested for safety, energy usage, and weight. And I actually have a couple of videos to show you. I'm actually going to show you a unsuccessful battery test first. A lithium-ion battery pack designed for use in the X-57 was put under a pressure test to see its ability to contain overheating, and what you'll see is the thermal damage that destroys the battery pack. So obviously what we're going to use is not, this is backwards, I should do the destructive one first. So the battery pack is here. You can see all the wiring. Typically, you should not have smoke coming from a battery, and hopefully your batteries don't explode. We'll go back and take a look at that. Let's go back and watch that one more time. So you can actually even see the battery flexing a little bit, releasing steam. There's a little spark. You say, Arby, why would you share something like this? The reason we share something like this is because we do the testing on the ground so that whenever we're flying in the air, we're safe. We push things to the limit on the ground so that we know when we fly that things are taken care of. So that is what we would consider a defective lithium-ion battery pack testing. And then we did, after that testing, we did some redesign. And in doing that redesign, we actually, I'm going to go ahead and hit play. Kids will feel so much better knowing that even NASA doesn't get it right. Right. Well, and so this one here, you can see that as we do the testing, now, we actually had to use like an infrared camera to be able to see the energy flux here, because they improved it so much that you couldn't tell. There was no steam, there was no smoke, there was no flex. And so they actually used infrared to be able to see the change in temperature as we push the battery to its limit. Jennifer, I think that's a great idea. Whenever you're talking engineering design process, it's not always about getting it right the first time through. You know, I often have looked at watching some of those that are racing towards space, Elon Musk and so forth, being able to, blow up rockets. And, you learn a lot from your failure. I mean, it's expensive to learn from your failure, but it is done. Autonomy of the battery, wind fight. I don't quite understand your question there about the autonomy of the battery. Can you expound on that? But again, what you can see here is a little change in color, indicating the difference in the temperature. You'll see at the very bottom, the scale here on the right-hand side, 40C as high as 100, and we nowhere near get there. So, really cool way of showing that. I do think it's important that we show the unsuccessful battery test before we show the actual successful one, because the unsuccessful came first. We pushed it to its limit. We saw the thermal damage. It destroyed the battery pack. So obviously, number of hours the battery will last. I'm not sure about the number of hours that it will last, but it will supply 32 kilowatt hours of energy. That's the only stat that I have at this point. How does electricity get from the batteries to the motors? Electricity is the flow of electrons. That's one of the subatomic particles that make up the atoms. And of course, if you teach physical science or chemistry, you know about electrons, protons, and neutrons. But electrons flow through a material called a conductor, and conductors make up the wiring in the X57 that carries electricity through the electric circuits to different parts of the plane. Batteries, like the ones used in the X57, need to be attached to an electric circuit for electricity to flow and do work. A simple electric circuit is a complete path that includes a power source, conductive material, and an item that requires energy, such as a light, a motor, or other instruments. Today, we're going to look at an activity where you'll be creating an electric circuit powered by a battery that will light an LED or LEDs if you choose to use two of them. That activity is called the X57 Maxwell Circuits Activity Guide. So as we take a look at this activity that you can do with your students will build a light-up paper helicopter by creating a paper circuit that uses copper foil tape and at least one LED and a battery. And again, like I say, you can use two LEDs in the particular model. You may have seen an older activity that NASA has had. So we're kind of putting an electric spin on the old rotomotor. And we'll talk more about that, and I'll share more about the rotomotor activity in terms of how simple it is. But basically, the rotomotor activity is taking a look at lift, fixed wings, which is a typical airplane, versus rotating wings like a helicopter. And so our paper model has rotor blades, and that literally provides the lift. But our focus is less about the lift this time and more about the electricity, because we're looking at the X57. So the rotor motor was a very simple design. This is the design here on the screen. And again, I'll have you a PDF copy of this at the end. And so you would cut on the solid lines and you would fold on the dotted. But what we're going to do here is less about the rotor motor and more about talking about circuits. So again, we're putting a new spin on that old motor rotor. So again, what is electricity? I'm not going to go into these slides, but these slides are some information that you could utilize within your classroom to provide some background for your students. But electricity is a natural phenomenon, and it's what powers the stuff that powers our electronic gadgets. And our goal is to understand how electricity flows from a power source through wires, lighting up an LED, spinning motors, or powering our communication devices. Some key vocabulary words, some definitions that might be helpful to know. Information here. Conductors and insulators. Again, if you teach physical science, these are some of the content that are applicable to you. But if you don't have that background, or if you teach at a lower grade level, this is some information that would be very useful to teach for your students. But conductivity, In talking about elements, it's a measure of how tightly the electrons are bound to an atom. The more ability that an element has to release those electrons, the more conductivity it has, and it tends to be a conductor. Elements that tend to be high conductors are metals. So if you'll think copper, silver, gold, those are excellent choices or good conductors. Insulators, those are elements with low conductivity. They don't tend to let go of their electrons. Things like glass, rubber, plastic, those are great insulators. So in talking about creating a circuit, it's important to know about conductors and insulators. In current electricity, that's the form of electricity which makes all of our electronic gizmos go. The form of electricity exists when charges are able to constantly flow. If you think about NASCAR, they sometimes call it a circuit, so it's a race car circuit. So as we're talking about a circuit for electricity, if you'll think about the cars on a racetrack, whether it's at Bristol or Daytona or even in Alabama and Talladega, those cars are going round and round and round. That is considered a closed circuit, and that allows the electricity to constantly flow. There's also static electricity, and that's where charges gather and remain at rest. Current electricity is dynamic, and charges are always on the move. Static electricity, and you could bring in some really cool activities with your students. If you've ever taken your feet and scooted them across the carpet and reached out your finger and shocked someone. You can also take the balloon and rub it up against your hair. But, one of the most dynamic examples of static discharge is lightning. Where static electricity comes from, you can take a balloon and rub a piece of wool up against it. The electrons are pulled from the wool to the balloon. Therefore, the balloon has more electrons. Having more electrons, which are negative, makes it negatively charged. And then the wool, which donated its electrons, becomes positively charged. Static electricity, that's how we get our photocopies. Did you know that? So just relating this to real world, a photocopy is utilizing the process of static electricity. So illuminating a light bulb. So here, this right here, this symbol right here, scientifically is how you draw a battery. So if you see this symbol in a diagram, that stands for a battery. Some of our diagrams, we just put in an actual, looking like a AA battery or something like that. But that symbol actually stands for a battery. Up top, this is the switch. So right now that's open. When it's open, the electricity does not flow. The light does not light up. But whenever that is closed, the electricity can flow through it, and it always travels negative to positive. And that's what allows the light to turn on. There are two ways for electricity to pass through two LEDs. Now, if you just have one LED, you just have a series circuit. But when you have multiple LEDs, which we are giving you the option of that on this activity, you can either set the circuit up in series or in parallel. Over on the left, you've got the arrows that show the only path through which the electricity can flow in a series circuit. Over on the right, you'll see that the arrows show both paths through which the electricity can flow in a parallel circuit. So now, what's the difference between series and parallel? Well, electricity flows out of the battery. It flows through the first LED and then into the second LED, always going from negative to positive. If you follow the arrows, it's always negative to positive. And yes, the LEDs have a positive and a negative side. We'll talk more about that in a second. But if you'll think about Christmas lights, if it is a series circuit, if one light bulb burns out, so if this light bulb here burns out, if it burns out, the electricity can no longer go through it, and so that means that neither light would light up. Now, a parallel circuit, which is what you have here, the electricity can go either through the first light or the second light, or both of them. And typically it goes both. But if one light burns out, it will not stop the electricity from continuing to flow through the one that is not burnt out. And this is whenever you have lights that are parallel. So personally, I prefer Christmas lights that are parallel, so that even if one light burns out, the rest of them continue to burn. Because I can remember as a kid, one of my assignments at Christmas with the lights was whenever there was an entire string not working, I got to remove every light and replace it with a new one until I figured out which light was bad. And if you had a situation where you had more than one light was bad, that was a really tough deal. But anyway, I always enjoyed that challenge, but that's the difference between parallel and series. And what we will be building, if you use two lights, will be a parallel circuit. So making the light up helicopter, you'll notice here, this is a little different than what we looked at a few minutes ago. You can see we've got the little, let's see if I got the pointer. There it is. Nope, I had the pointer. There it is. You can see A, B, C, D, E, F, G, maybe not G. So A, B, C, D, E, F. And with those letters, what that gray area is where you will put copper foil tape. So this is the helicopter template you'll need. You'll need about 16 1/4 strip of double-sided conductive 1/4-inch copper foil tape, up to 2 5mm LEDs. You can just use one if you like, but 2 if you want to do a parallel circuit. We recommend the CR2032 battery. Then you'll need a ruler, scissors, and either a paper clip or small binder clip to help add some weight once we're finished. So as you start out, just like with the old rotor motor activity, cut around the outer rectangle of the helicopter, so where the solid lines are cut, and remember where the dotted lines are, you're going to fold. And then those gray lines, that's where you're going to use, and that did not work out right. Sorry, that picture does not, the picture that you will download will have the correct one, but you're going to cut the individual pieces of copper tape according to that appropriate length. And using those particular lengths, you will then fill out A, B, C, D, E, and F. Now, I will note that these 4 pieces here at the end, those do not go into the original setup here, because those will be used to affix the light bulbs to the paper a little bit later on. So you'll fold the flaps labeled X and Y towards the back as shown. The folds should be on the dashed lines, and I highly recommend running your finger down the fold to make sure the crease is tight. To add the LED lights, this is where you're going to use those 4 little strips that I talked about. Look at the LEDs. Again, you can use 1 or 2, but the LED light wires will need to connect to the 2 copper tape strips, which will complete that parallel circuit. Note that each color LED needs a different amount of electricity, so it's best to have both LEDs the same color. But for the sake of our demonstration here, we have shown you 2 different colors. It is possible to have 2. Just make sure that your battery is strong enough to be able to pull the amount of electricity needed for that. That's something I learned in the process. I didn't know that different color LEDs actually required different amounts of electricity. It was a learning process for me. More about LEDs. The LED lights are polar, meaning that one side is positive and one side is negative. Typically with the LED, you can look at the length of each side of the LED. You'll notice the positive length is longer and the negative side is shorter. Also, some LEDs have a flat side to their casing and the flat side is negative. In doing the handout for this activity, we did not include that because we are recommending 5mm LED lights, And in my opinion, that's a little tough to be able to look and see which side is flat and which side is not flat. But it is true that some of the LEDs have that. So adding the LEDs, the long wire must be connected to the positively charged copper tape on the left, and the short wire connected to the negatively charged copper tape on the right, because remember, it's always flowing negative to positive. You'll use those half-inch pieces of copper tape to connect the wire, and when bending the wires, try to bend them outward so that each wire overlaps the copper tape lines on the helicopter blades. And I'll show you what that's talking about. You can see that as we put them there, that the wiring is here, so we were able to simply cover it. Same deal down here and over here. If you're unable to identify the long and short wires of the LED, a quick internet search can show you other ways to identify them. You can also test them before taping the LEDs to the paper. If taking the LED, whenever you connect it to the battery, if that doesn't work, flip it, because it is either positive or negative. So hopefully it's not too many different times that you have to test it. Again, I apologize about this picture. The one that you will download is correct. This is just Adobe Connect and PowerPoint not working well together. I'm sorry. But you will place your battery on the circle in the helicopter template. It's important that the positive side of the battery is down, touching the paper and the tape. And to determine which side of the battery is positive, you can look closely at the face of the battery to see which side is marked with the positive or the plus sign. Typically, the positive is marked. The negative is not always marked on all batteries, but sometimes they are marked on both sides. You'll fold the bottom part over the battery up. So you can see this part here, that folds up, and it almost somewhat creates a pocket for the battery so that the circuit is complete. That's connecting the positive to one side of the battery and the negative to the other. And when you do this, the LED should light up. And if you put a paper clip or a binder clip on the bottom of the helicopter there, covering the battery, it'll help to keep that circuit intact so that whenever you toss it up in the air for it to fly, that it stays lit up. The final touches, fold the two blades in opposite directions along the dashed lines. Again, you may want to run your fingers across them to create that crease. For the blade that has the copper tape on it, make sure the tape is facing upwards. And then give it a toss and watch it fly. If you have issues with the lights lighting up, which is common whenever you're working with paper circuits, make sure you check all your connections, in particular around the LED leads, in other words, where those wires come in contact with the tape. Check the alignment with the battery. Whenever you fold it, did the battery shift a little bit? Are there any broken places in the copper tape? Use more tape to reinforce a connection if necessary. Push down on the tape to make sure it's properly adhered to both the paper and other pieces of tape. Sometimes a little firm rubbing over of your hand along the lines of the tape helps out. And there should be plenty of overlap with pieces of tape to ensure a solid circuit. But the positive side should never touch the negative side. If the positive touches the negative side, that creates a short circuit, and you'll never get it to light up if there's a short circuit. Make sure you have a complete and proper circuit. That means the positive end of the LEDs must match up with the positive ends of the battery. So if whichever side of the battery is coming out positive, needs to be the same size as positive with the lights. One piece of copper tape should make solid contact with one side of the button battery, and the second piece should make contact with the other side. And again, make sure that once the battery is folded, that they are securely together. And I find using those paper clips, or even I call them the bulldog binder clips, work really well. Try flipping the battery over. If the LED was put in backwards, meaning the positive and negative parts were reversed, you can reverse the battery and it will work. If you're using two LEDs, Make sure both LEDs are oriented the same direction. In other words, both negative sides are touching the same piece of copper, and vice versa. Some LEDs or batteries might not be working correctly, so feel free to try a different battery or even a different LED. Directions that we have given you today are for double-sided conductive copper foil tape. And that can be purchased from a number of online retailers. Because this type of tape is conductive on both sides, sticking one piece on top of another creates an electrical connection. If you happen to get copper foil tape that is only conductive on one side, you'll need to have one piece of tape that goes all the way from the battery to the LED. And to do this, you'll need to create folds where the tape changes direction. An internet search can help you with using directions on how to do that. But the most common is just use that double-sided conductive copper foil tape. Further experiments. You can try adjusting the circuit by different numbers. You can use different colors, different sizes of LEDs. You can also use different sizes of the button batteries. LEDs are commonly found in 3, 5, and 10 millimeter sizes. The smaller sizes have less mass. The larger ones have more mass. And obviously, if you use 1 3 millimeter or 2 3 millimeters, that would be 6 millimeters. So, I mean, you know, you can adjust some with the weights there and see the difference that it makes. Obviously, the smaller has less and the larger has more. There's different types of LEDs available. There are some that are made wearable, lily pad type LEDs. You can get stickers that are LEDs. They actually have the circuitry built into it and so much more. You can even use LEDs from a string of lights. You can adjust the helicopter itself to change the speed with which it rotates and falls. Try folding or cutting the blades to change their shapes. You can also try folding the blades at different angles. You can also attach different weights to help make the helicopter heavier or lighter. Use different paper that instead of, you could use cardstock as opposed to just copier paper. The larger paper will also make it heavier. You can add more weight to the helicopter. You can do that by simply adding more paper clips to the bottom of it. You can use other conductive materials to make the circuit. Lots of materials are conductive, so try to create a different type of circuit. There's the electrically conductive paint or even a conductive pen. You can actually draw your own circuit with that. You know, can you connect 2 LEDs in a series circuit so that they both light up, whereas what we've provided would be a parallel one? Can you think of anything else that you could change? You can even allow the students to even decorate or color them if you wanted. The possibilities truly are limitless. And I think, you know, if you use the old model with the old rotor motor, let them predict what's going to happen. Maybe even let them experiment some flying like this before you put the electric circuit on there. Extensions, you can even determine the number of rotations. The instructions are there by using cassette tape or even just a type of ribbon. You step on it, then the number of twists that you get in it as it goes down allows you to count the total number of twists. The total number of twists would equal the total number of rotations that it went. There are additional activities. There's the X57 Educator Student Activity Guide. I know it looks like just what we had with the electric circuits, but this is it actually contains 4 different lessons. And the first lesson is about constructing the battery, where you can make your own battery. You can digitally test portable electronic device, talk about the physics of flight, and look at teamwork. NASA Aeronautics has additional resources, and this page here gives you more information. There's aeronautics for pre-K, there's Museum in a Box, there's some ebooks, there's some leveled readers. You can see our Aeronautics at Home page, as well as the Next Gen STEM Aeronautics website. There is an entire aeronautics STEM module, which information is here and includes some of the information that we've already shared as well. If you haven't signed up for NASA Express, it's NASA's main way of reaching out to educators and students. A weekly email is sent out with opportunities for educator professional development, reminding you of webinars like this, student design challenges, internships, and so much more. You can also join us on the Educators Facebook page. Thank you for attending.